Maybe you've heard someone say that you need to shuffle a deck of cards 7 times before it's truly random. But is that actually true? Well, if you clicked on this video while shuffling your deck and you just want to know when to stop, here's a table showing the distance from perfect randomness after each number of shuffles. 7 appears as the first number of shuffles where the deck is less than 50% different from perfect randomness. For most games, this is good enough, but it isn't actually perfectly random. By the time you hit 10 shuffles though, the deck is less than 5% different from perfect randomness, which should definitely suffice for any game played by humans. On the other hand, if you only shuffle 3 or 4 times, the deck is almost 100% different from perfect randomness, which means that some humans could probably take advantage of the lack of randomness here. Okay, if you're still here, I'm guessing you have some questions. How do I know that this table is actually correct? And what does the distance from perfect randomness even mean? Well, in this video, we will answer both of these questions. Actually, we won't quite reproduce the table shown here, but we will come pretty close. Along the way, we'll discuss 2 different kinds of shuffles, understand the total variation distance between 2 probability distributions, and use the coupling technique to get an upper bound for this distance. First, a basic question. What even is shuffling? Well, it's a way to introduce randomness to a deck of cards. Each time we shuffle, we add a little bit of randomness, and we hope that eventually the arrangement of the cards in the deck will be random enough. In this framework, we can consider a very basic type of shuffle called top to random. Just take a card off the top of the deck and insert it somewhere in the deck at random. If you only do this once, then clearly the deck is not very randomized. But maybe if you do it a couple hundred times, it will be. Of course, this is not how people actually shuffle, and we will discuss a much more realistic model for shuffling later in the video, but the top to random shuffle will help us understand what's going on in a simplified setting. Let's simplify again and consider a deck with only 3 cards. There are 6 possible arrangements of the cards, as shown here. Let's suppose that we start with the arrangement 1, 2, 3. After we do one top to random shuffle, the arrangement could be one of these 3 possibilities, each one equally likely. Now I'll draw some arrows connecting each arrangement to the other 2 arrangements that could be reached after one top to random shuffle. Each time we do a top to random shuffle, the probability mass on each arrangement is split into 3 pieces. 2 of the pieces travel along the 2 arrows and one of them stays in place, since we could place the top card back on top where it started. Notice that as we continue to shuffle, and the probability mass keeps being distributed in this way, it eventually looks like every arrangement is pretty much equally likely. This is what we mean by perfect randomness, the uniform distribution on all possible arrangements of the cards. How can we tell how close we are to perfect randomness? Well, mathematicians have invented a notion of distance between 2 probability distributions. So what we really want to know is the distance between the uniform distribution and the distribution of the arrangements after some number of shuffles. Here's a bit of notation to help us. Mu will denote a probability distribution on an outcome space omega. For instance, omega could be the set of all possible arrangements of a deck of cards. A probability distribution tells you how likely each outcome is. So if mu denotes the uniform distribution on the 6 possible arrangements of 3 cards, then mu assigns probability mass 1/6 for every arrangement in omega. On the other hand, if mu is the distribution of the arrangements after one step of the top to random shuffle, then mu assigns probability mass 1/3 to these 3 arrangements and 0 to these 3 arrangements. Now, if we have any 2 probability distributions mu1 and mu2 on the same outcome space omega, then one way to measure the distance between mu1 and mu2 is by using the following formula. For each possible outcome, we compare the probability of that outcome in the distribution mu1 with that in the distribution mu2. Sum over all possible outcomes and divide by 2 to get the distance between mu1 and mu2. This notion of distance is called the total variation distance, which is why we denote it by dTV. This formula is a little daunting, but there are actually 2 much better ways to think about the total variation distance. First, the total variation distance is equal to the maximal difference in the probabilities of some event. An event is just a subset of the outcome space, and the probability of an event is simply the sum of the probability mass at every outcome in the event. For instance, one possible event is the event that card 2 is above card 3. Under the uniform distribution, this event has probability 1/2, since card 2 is equally likely to be above or below card 3. On the other hand, after one step of the top to random shuffle, card 2 is always above card 3. This means that the total variation distance between these two distributions is at least 1/2. This gives a better interpretation of the table that I showed at the beginning. In particular, it means that after only 6 shuffles, there is some event which has a 60% higher chance of occurring than it should have if the deck was perfectly random. With 3 or 4 shuffles, there is some event which will happen almost every time, when it should almost never happen if the deck was perfectly random. This event could be used to gain an unfair advantage if the state of the deck before shuffling was known, and if the event in question is relevant for the game being played. I should be able to win on the next turn as long as at least 9% of the not necessarily contiguous sequences of length 4 are still sorted with respect to the standard ordering of the cards. This should happen since you only shuffled 3 times and... Wait, was the deck in the standard order before you started shuffling?
Go fish.
Yeah, in a casual game where you don't know the state of the deck beforehand, it really doesn't matter how many times you shuffle. The point of randomness in this context is its unpredictability, and if nobody's paying too close attention, a few shuffles for posterity are good enough. But let's assume for the rest of the video that you do care about mathematically perfect randomness. Maybe you've got a high-stakes poker game, or maybe you just like math. Either way, let's finish our discussion of the total variation distance. The other way to think of the total variation distance is in terms of random variables. Let me briefly say that a random variable should be thought of as some random outcome, and every random variable has a distribution which tells you how likely each outcome is, but multiple different random variables can have the same distribution. For example, if I flip a fair coin 5 times, the number of heads and the number of tails both have the same distribution, which is the binomial distribution with parameters 5 and 1/2. However, clearly the number of heads is not equal to the number of tails. Now, the total variation distance is equal to the minimum over all possible random variables x1 and x2, which have the distributions mu1 and mu2 respectively, of the probability that x1 is not equal to x2. This is a bit subtle, but the pair of random variables should be thought of as a way to sample from the two distributions simultaneously, although not necessarily independently. This is also called a coupling of the two distributions. Since this definition is probably the most confusing, and it's also the one we'll use the most, let's work through an example to see what's going on. The simplest possible random situation is a coin flip. So let's calculate the total variation distance between two different, possibly unfair, coin flip distributions, using all 3 of the definitions we discussed. Suppose the first distribution has probability p of coming up heads, and the second distribution has probability q. We can assume that p is at least as big as q for simplicity, and we'll call these distributions mu p and mu q respectively. By the first definition, the distance between mu p and mu q is 1/2 times p minus q plus 1 minus q minus 1 minus p, which simplifies to just p minus q. The second definition tells us that any event gives a lower bound for the distance. Let's use the event that the coin comes up heads. Under mu p, this event has probability p, and under mu q, it has probability q. So the second definition tells us that the distance is at least p minus q. Of course, we know that it's equal to p minus q from the previous calculation, and so we know that the event we considered is optimal. Finally, let's discuss the third definition. What even is a coupling between mu p and mu q? Intuitively speaking, a coupling is a way to flip both coins at once. Of course, we could just flip both coins independently of one another, and then we get a probability distribution on pairs of outcomes like this. Under the independent coupling, the probability of any pair of outcomes is just the product of the probabilities for both outcomes. Since the formula has a minimum, this coupling gives an upper bound, which is the probability that the two coins are unequal under this coupling. Here, the probability that they're unequal is the sum of these two entries of the table, p times 1 minus q and 1 minus p times q. However, if you do a bit of algebra, you can see that this is strictly greater than p minus q. In other words, flipping the two coins independently is not the optimal coupling. Instead, let's introduce another background random variable, which will just be a uniform random number between 0 and 1. We can simulate the first coin by saying that it should come up heads if the random number is less than p, and tails if it's greater than p. This gives a coin flip which has probability p to come up heads, which is exactly what we want. We can also simulate the second coin by saying that it's heads if the random number is less than q and tails otherwise. Crucially, we are using the same random number to simulate both coins. This gives a coupling between the two coins, a way to flip them both at once, but now they're not independent because they're simulated using a common source of randomness. Now let's calculate the probability that the two coins are unequal under this coupling. First, if the random number is less than q, then both coins come up heads, and if the number is greater than p, then both coins come up tails. So the only time they disagree is when the random number is between q and p, and the probability of this happening is p minus q. By previous calculations, this is the total variation distance between the two coin flips, and so we know that we've found an optimal coupling this time. And this is indicative of a general phenomenon. Good couplings generally arise when you can simulate two random variables using a common source of randomness. Hopefully this example illustrated why it's nice to have all three of these definitions for total variation distance, especially the second and third ones. Since they're given in terms of a maximum or a minimum, any event that you can think of gives a lower bound for the distance, and any coupling you can think of gives an upper bound. In more complicated settings, it might be quite difficult to calculate the total variation distance exactly using the first definition, since the number of outcomes might be astronomical, and you might not even know how to calculate the probability of each outcome. In these cases, the second and third definitions are often much more practical. In fact, in the rest of this video, we will just be constructing couplings in order to get upper bounds on the distance in our card shuffling examples. To avoid having to say the unwieldy phrase, total variation distance between the uniform distribution and the distribution of arrangements after t shuffles, over and over again throughout the video, I'll abbreviate that to just d of t, with a superscript indicating which shuffle we're considering. For now, it will be d top to random, and I'll just call it the distance after t shuffles. Also, I will use n to denote the number of cards in the deck, so really this distance depends on n as well. Once we have an upper bound on the distance after t shuffles, we will be able to invert the expression we get to obtain an upper bound on the number of times we need to shuffle in order to achieve a particular distance, say epsilon. This is called the mixing time, and it should be thought of as a function of epsilon that also depends on n. Before we start constructing our couplings, there is one small trick we need to apply. Let's go back to the network that determines which card arrangements get turned into which other arrangements after doing one shuffle. And let's try reversing all of the arrows. This corresponds to reversing the shuffle, i.e. performing a random to top shuffle instead. But look, the structure of the network is exactly the same as before. Of course, the positions of the arrangements relative to one another in the network are slightly different, but if we forget about what the nodes of this network represent, then we can see that the two networks are isomorphic. And since we always just sum over all the outcomes when calculating the total variation distance, this means that the distance after t top to random shuffles is the same as the distance after t random to top shuffles. If you want to know exactly why this happens, let me just say that what we have here is something called a random walk on a group. And if you know what a group is, you'll know that groups are very symmetric objects, and this reversal isomorphism is just one way in which this symmetry manifests. All this is to say that we really only need to analyze the random to top shuffle. So we will be constructing a coupling to get an upper bound for the distance after t random to top shuffles. One important thing to notice here is that if we start with a perfectly random deck, then doing one step of this shuffle does not make the deck less random. So it stays uniform as we shuffle it. This means that we can build our coupling step by step. We will start with the unshuffled deck and the perfectly random deck, and couple each individual shuffle that we do. Let's do this face up with a small deck of cards so we can see what's going on. At each step, we'll choose a random card from the unshuffled deck and put it on top. We'll do the same with the perfectly random deck, but we'll make sure to choose the same card in both decks. Now, in each deck taken individually, a uniformly random card is being chosen to be placed on top. But we're simulating both choices using the same source of randomness. We first randomly pick the identity of the card that will go on top, and then do the shuffle in both decks with the same card. After we do this once, notice that the top card is the same in both decks. If we do it again, then the top two cards are the same, unless we pick the top card again, and as we keep going, more and more of the top few cards will agree, and eventually the two decks will have the same arrangement. As we continue shuffling after this point, the decks will always stay in the same arrangement, even as individually they continue to be shuffled. Remember, we want to find the probability that the two decks don't have the same arrangement. After we choose a particular card to place on top, then for the rest of the shuffling, that card will be in the same position in both decks. So the decks will certainly have the same arrangement after we have chosen every card at least once. They could agree sooner, but they might not. We can only guarantee that they agree after every card is chosen at least once. So the distance after T shuffles is at most the probability that we haven't yet chosen every card in our T choices. This is an instance of the coupon collector problem, and if you've seen that before, then you'll know that the expected number of random to top shuffles it will take for the decks to be in perfect alignment is about n log n, if we have n cards in the deck. Let's be a bit more careful though. If we haven't yet chosen every card, then there is some card which has not yet been chosen. So, the probability that we haven't yet chosen every card is at most the sum of the probabilities that each individual card has not yet been chosen. For each individual card, the probability that we don't choose it is n-1 by n raised to the t, since we have to have chosen a different card at each of the t steps. So the sum becomes n times 1 minus 1 by n to the t. This could be our final upper bound for the distance after t shuffles, but since 1 plus x is upper bounded by e to the x, I'll just upper bound this by n times e to the minus t over n. Trust me, this will make the algebra that I'm about to do a lot simpler. If we just want to know how many shuffles we need to do, we can set this equal to the desired distance from the uniform distribution and solve for t. Specifically, if we want to get within epsilon of perfect randomness, we can get there with at most n log n plus n log 1 over epsilon random to top shuffles. And of course, the same upper bound holds for the top to random shuffle. In other words, the mixing time of the top to random shuffle in a deck with n cards is at most n log n plus n log 1 over epsilon. For a standard deck of cards with n equals 52, if we want to get within 50% total variation distance from perfect randomness, this tells us that we only need to do 242 shuffles. 32, 233, 234, 235, Where are you going? I'm almost done. Well, I suppose that's why nobody actually shuffles this way. Let's think about a more realistic model. Usually when people shuffle a deck, they do a riffle shuffle, like this. A riffle shuffle has two steps. First, cut the deck roughly in half, and then riffle the two halves together, interleaving the cards as you go. To model cutting a deck with n cards roughly in half, let's use a binomial random variable with parameters n and 1/2 to represent the size of one of the pieces. This distribution typically represents the number of heads in n fair coin flips, so it's pretty close to n over 2 most of the time. But there are fluctuations around this value, which makes sense because we aren't always able to cut the deck perfectly in half. For n equals 52, each half will typically have between 22 and 30 cards, which seems pretty reasonable. After this, in order to riffle the two pieces together, we place the cards down from one side at a time, choosing the side at random with probability proportional to the number of cards left in that side. This also seems like a reasonable way to do things, and it turns out that it produces a uniformly random interleaving of the two halves. And as with top to random, this shuffle is better understood if we reverse everything. One step of the backwards riffle shuffle amounts to choosing a uniformly random subset of the cards and putting them all on top. Now we're ready to construct a coupling like we did for the random to top shuffle. This time, we just make sure to choose all of the same cards in both decks. Again, each deck individually is choosing a uniformly random subset, but they will just happen to be the same subset in both decks. After we put the chosen subset on top, the decks are making some progress towards being in the same arrangement, but unlike random to top where each card is in the same position after it's been chosen, it's a bit less clear that progress is being made. To elucidate this, let's switch to some blank cards so that we can write on them. If a card is in the subset that we choose, we'll write a 0 on it, and otherwise we'll write a 1. Then all the 0 labeled cards go to the top, and the 1s go to the bottom. In the next shuffle, we'll do that again, writing a 0 or 1 to the left of the previous number. Notice now that if we interpret these two bits as a number in binary, then the cards are arranged in increasing order. Additionally, each card has the same binary number written on it in both decks. Now, if a card has a binary number different from any other card, then the position of this card is the same in both decks. But if there are multiple cards with the same binary number, then these cards might not be in exactly the same position in both decks, because we can't say anything definitive about the relative order of cards with the same number. Nevertheless, if we keep applying backwards riffle shuffles and writing these bits, then eventually every card will have a unique binary number, and so the decks will be in the same arrangement. How long does it take for this to happen? Well, after T shuffles, each card will have a binary number that is uniformly random among all binary numbers with T bits. There are 2 to the T of these numbers, and so what we are really asking is if we sample n things with replacement from 2 to the T possibilities, what is the probability that we get a duplicate somewhere? This is an instance of the birthday problem, and so if you know about that, you might have some guesses, but again, we'll do our own analysis. For there to be a duplicate somewhere, there must be a pair of distinct cards which have the same number. So, the probability that there is a duplicate somewhere is at most the sum of the probabilities for each pair of distinct cards to have the same number. Since the numbers written on the cards are independent of one another, and each one is a uniformly random bit string with T bits, all of these probabilities are 1 over 2 to the T. There are n choose 2 summands here, which I'll just upper bound by n squared over 2, and so we find that the probability that we see at least one duplicate is upper bounded by n squared over 2 to the T plus 1. So the probability that the two decks have not yet reached agreement by time t is at most n squared over 2 to the T plus 1, and this means that the distance after T riffle shuffles is at most n squared over 2 to the T plus 1. Turning this around again, we find that the mixing time of the riffle shuffle is at most 2 times log base 2 of n plus log base 2 of 1 over epsilon minus 1. What does this give us for n equals 52, a standard deck of cards, if we want to be within 50% total variation distance from perfect randomness? Plugging these numbers in, we see that we need to do at most 12 shuffles. This is higher than the 7 shuffles that the previous table showed us, which makes sense because we didn't actually compute the total variation distance, we just got an upper bound for it. To get the true total variation distance takes a lot more work. That was done in a paper by Dave Bayer and Percy Diaconis, which is where I got this table in the first place. In the paper, they compute the exact probability distribution of the card arrangements after any number of riffle shuffles, and then use definition 1 for the total variation distance. This is pretty difficult, and they say that their proof relies on the analysis of a card trick and the determination of the idempotence of a natural commutative subalgebra in the symmetric group algebra. If that's the kind of thing you're into, then you can go ahead and give this paper a read. But I want to point out that we already got pretty close to their result, at least in an asymptotic sense. Their paper says that the mixing time of the riffle shuffle is about 3/2 times log base 2 of n. Remember, we got 2 times log base 2 of n ourselves without too much work. So, if you don't want to read about determining the idempotence of commutative subalgebras in the symmetric group algebra, well, you might as well just shuffle 5 more times.